Hey everyone, my name is Max. Just like Anna told you, I'm a head of engineering at Near. And for those of you who don't know, Near is a sharded proof of stake blockchain with a special focus on developer friendliness. And sharding is just one of the ways how we achieve developer friendliness because sharding allows us to be scalable, like high TPS, low confirmation time, cheap transactions, and so on. But another way how we achieve developer friendliness is by using a WebAssembly virtual machine, because WebAssembly allows people to develop contracts in a large variety of languages. So currently we support two languages, Rust and AssemblyScript. So most of you are familiar with Rust, and most of the WebAssembly enabled blockchains, they actually use Rust as their primary smart contract development language for many good reasons. So one of them is that Rust is the first class citizen as a WebAssembly language, not surprisingly, because the community that develops Wasm and Rust is heavily overlapping. So it's frequently the same people who work on Rust and Wasm. Also, Rust is a very safe language. As we all know, it has strong typing and lifetimes and prevents all kind of ways of shooting yourself in the foot. So that's why we default to Rust as our primary smart contract language. But we also allow people developing an AssemblyScript. And for those of you who don't know, AssemblyScript is a dialect of TypeScript. It has been developed by a small group of people that we are the biggest sponsor of. And what they're trying to do, they try to get the right balance between having a developer-friendly language for people coming from the web and mobile development. So many people coming from web development, they're already familiar with TypeScript. So AssemblyScript is just a dialect of TypeScript. It looks almost exactly the same as TypeScript, but it has some extra annotations for type safety and whatnot. And it tries to also be as close to WebAssembly as possible. So it tries to be easier to compile to WebAssembly than TypeScript. And many developers come into our blockchain. They're with only the knowledge of TypeScript, they're able to develop an end-to-end decentralized application just in TypeScript, like write a contract in AssemblyScript, front end in TypeScript, they deploy it on the mainnet in a matter of minutes or hours, depending on the complexity of their project. The other two languages that we are going to support very soon as our smart contract development languages is Grain and Zig. So for those of you who don't know Grain, Grain is the very recent language that gained quite a lot of popularity because it tries to be a web development focused language, but as a language that is also very easy and native, easy to compile to WebAssembly and native to us, native to WebAssembly development. We are also sponsoring them, and they have already a beta SDK on Near that is gonna soon to be productionized. And Grain also strikes a really good balance between like Rust and TypeScript kind of language. It doesn't have manual memory management, which is kind of a strength of Rust, because with manual memory management, you don't have this spikes of CPU usage when your garbage collector kicks in. But for most of the languages, they're going to explain to you later, that have non-manual memory management, we actually just disable garbage collection because smart contracts are short-lived anyway, and we can afford to never deallocate memory in the first place. So the Grain is the case coming very, very soon in the next week or a couple of weeks. And Zig is another language that we've been developing SDK for. Zig is also quite popular. It compiles to WebAssembly quite easily. And yeah, so we're going to have 4 languages as a smart contract languages on Near blockchain soon. So the question is, how many languages are we going to have in the near future? What are our plans? And our plans are to have like every single language that compiles to WebAssembly, and every language that we can lay our hands on as a language for smart contract development on Near. And it's just a matter of time and a matter of the resources, but we're going to get to all of them. We have already been experimenting with C++, Python, Java, Go, and there are various reasons why when we don't have SDKs for all of them. Specifically with C++, it's because we are intimidated by its complexity, specifically of the M scripting. M scripting has been around for quite a long time. It's quite a big code base. So once we get more clarity and confidence with using app scripting, we're going to have C++ SDK on near. Java, Python, and Go turn out to be very heavy in the compilation to WebAssembly. Specifically, Python programs, they are order of magnitude larger when compiled to WebAssembly than equivalent programs written in Rust. And that's because Python is not meant to be compiled to WebAssembly. It has pretty heavy runtime. And the contracts that would usually be like 100,000 bytes in size, they become like 2 megabytes in size when written in Python and compiled to WebAssembly. But we'll figure something out in the future. We might narrow down these languages, again, use some kind of a dialect to make them easier to compile to WebAssembly, or we might even raise the maximum contract size on near blockchain to be able to accommodate all of these languages. So if you're a fan of any specific WebAssembly language, whether it's a general purpose language like Python, or like a new language like Rain or Zig, please write us, and we might work together on SDK for near. There are various virtual machines that we are using to run WebAssembly programs at near. So right now we're using Wasm and SinglePass and Wasm Time and Lightbeam. So these are both non-optimizing backends for WebAssembly compilation. There are reasons why we don't want to use optimizing compilers. First of all, is that optimizing compilers like LVM and CraneLift, they're quite large in their code base size, and we want to be very confident with the WebAssembly backend that we integrate into our blockchain client, and so we just try to stay away from them for now. But also optimizing compilers, they have much more complex behavior. They're prone to compiler bombs sometimes, and we just don't want to deal with it yet. So we still use Wasm and SinglePass and Wasm Time plus Lightbeam right now. Right now we're using Wasm 0.17 as our default execution environment, but we are slowly migrating to Wasm 2.0. Wasm 2.0 has faster compilation, time of loading the module into memory, and faster execution of WebAssembly code in general. So we're going to have at least twice faster contracts once we migrate to Wasm 2.0. We've just been extra careful with fixing all safety issues in Wasm 2.0 before migrating to it. We also have Wasm Time and Lightbeam integrated into near blockchain. We don't use it by default. However, any validator can switch to using Wasm Time plus Lightbeam if they want to. And the reason we have it there is just in case we find any kind of bug in Wasm and SinglePass, we will be able to signal to our validators to switch to Wasm Time plus Lightbeam while we're fixing this bug, but this hasn't happened yet. Surprisingly, even though Wasm and SinglePass and Wasm Time plus Lightbeam have very different code bases, entirely different approaches to compilation, Lightbeam as a streaming compiler, their performance, at least for Wasm 0.17, is quite similar on most of our benchmarks. So that was a very interesting discovery. We are also looking into the interpreters. So Parity has been used in Wasm since the beginning. There is also Wasm 3, very popular interpreter right now. We might be looking into using them because the advantage of the interpreter is that they have a very simple warm-up, unlike the compilers that need a complex module loading before you can start executing the smart contracts. Interpreters are really easy to start up, even though they're much slower when you actually execute the Wasm code. So we might add them in the future and allow people to choose which Wasm virtual machine to use when executing the smart contract. So they might be able to use interpreters for really, really tiny contracts and pay even smaller fees for them. We're also going to be looking into the optimizing compilers too. We talked to CraneLift core developers, and it seems like there is a way to run CraneLift in an optimizing way get rid of some optimization stages. I need to make it also smaller in code size. That might allow us to have crane lift as another WebAssembly backend for WebAssembly execution at near. The interesting thing is that running sharded proof of stake blockchain actually has strong advantages. So one of them is that we have an inherent incentive for validators to run multiple virtual machines. So right now, you know that some virtual machines, they have implementations of their protocol stack in different languages. But what frequently happens is validators do not really have incentive to diversify the clients that they're using. And frequently the network just converges to one client which is, you know, the cheapest or the faster, so whatever has better configuration parameters, which undermines the whole point of having multiple implementations, because you know, if 80% of validators are running the same client, then, you know, if you have coordinated error, it's going to go down anyway. With sharded blockchains, you frequently have a mechanism of slashing that allows you to run shards optimistically, where you kind of put faith into the sharding validators on each shard to produce valid blocks, but then at the same time you supervise them, and if you notice that the blocks are invalid, you slash them. So what has happened on some shard blockchains, and what we want to avoid, is that when slashing happens because of some bug, which hasn't happened on Near. We also haven't enabled sharding yet, but if validators want to really avoid being slashed because there is a bug in the code, or because they have messed up the DevOps, the setup, then they might have an incentive to run multiple clients with different implementations side by side. And if they disagree on the block production, then they would terminate their clients without producing any block. So there is an inherent incentive on the blockchains with slashing for the validators to run multiple clients. And maybe even the same client, but the same client that uses different virtual machines. It can also be an alternative for validators. So there are many difficulties with running WebAssembly virtual machines on the safety side that we have discovered. So the biggest one is the strict separation of deterministic and ephemeral errors. So what I mean by deterministic versus ephemeral errors is that deterministic error is the kind of an error that has been introduced by the contract developer. Let's say they have written a program that, you know, does division by 0 or exceeds the maximum allowed stack size in WebAssembly. Non-deterministic ephemeral error is the stuff that happens because there is a fluke. I don't know, like you run in some other programs on your cloud instance, and, you know, node runs out of memory, or you have disk corruption. And this is something that can be happening just only on your validator machine, or it can be happening on, for instance, on all validator machines that run in the same kernel version. This is something that has happened on one of our testnets. And so it's extremely important to be able to separate these errors that are being piped to you by the virtual machine into these two strict categories. Because if you make a mistake and you confuse deterministic error for ephemeral because of some bug in a virtual machine, then what might happen is that someone might be able to craft a smart contract that triggers this deterministic error and causes all the nodes think that there is an ephemeral error. And what we do with ephemeral errors is that we just shut down the node. We don't want to have a special recovery mechanism when you have a disk corruption happening. So we just shut down the node in this case, and if we make a mistake and miscategorize deterministic error for ephemeral, then someone can crash the entire network, which hopefully is not possible to happen. If you miscategorize ephemeral error for deterministic error, then what might happen is that some nodes, they might think that they produced a valid block, but it's actually invalid. And if this happens on all, let's say, versions of the same kernel across a subset of the nodes in your network, then you might have a network split, or, you know, a bunch of nodes being kicked out, which is also nasty and you don't want to happen. So it's the top of our mind to separate deterministic and ephemeral errors very precisely for the Wasm virtual machines, and occupies a lot of our time doing it correctly. Full compatibility with Wasm standard will also turn out to be not super trivial, because there are very tiny corner cases around trap handling that we found out are not handled precisely on Wasm virtual machines. And this is something that we noticed only post factum. Forward compatibility with Wasm standard is also important for us. So I'm going to be talking later on how we do the gas injector and instrumentation of Wasm contracts. And the new way of doing the gas injector makes a strong assumption that certain parts of Wasm standard are not going to be extended in the future. And so that's basically an assumption of forward compatibility Wasm standard that we're going to talk about later. Then you also want to canonicalize the floats. This is something that we do for all our contracts. Initially, we decided to just sanitize our contracts and prohibit deploying the contracts on near blockchain that use the floats. But we very, very quickly found out that this leads to a very bad developer experience, because like Rust developers, they just want to import libraries when they develop smart contracts. And surprisingly, even if you're importing some library that doesn't use floats for like math operations, let's say you're importing some cryptographic library, it still might be the case that you will have some float operations in there because of how, for instance, Rust does string formatting, for panics. So we decided to allow floats in near smart contract, but now we canonicalize them. And finally, this entangled implementation of Wasm virtual machine from the protocol turned out to be also not super trivial. There are some minute details about how the stack handling is being done by Wasm virtual machines, or how Wasm virtual machines interact with your instrumentation that made some of these details leak into our protocol spec and tie us to a specific implementation of the Wasm virtual machine that we're currently slowly removing. We also had lots of challenges with determinism in the virtual machine. Well, first of all, as all of you know here, the worst case scenario in the blockchain space is basically what determines the fees. Usually, it's not the best case scenario, because if you optimize your fees to target for the best case scenario, then your blockchain is going to be vulnerable. Someone might be able to trigger the worst case scenario. So yeah, the worst case scenarios dictate the fees, which dictate TPS on your blockchain at the end of the day. You can try to special case best case scenario and say, for instance, that if your contract doesn't hit some corner cases, then the fees are generally lower. Unfortunately, that leads to bad DevX. Well, first of all, your fees might be unpredictable. So if developers find out that in certain cases, the smart contract execution is much more expensive than in other cases based on some super low level internal mechanism in how WebAssembly virtual machine functions, then DevX is going to be pretty bad. But also special case and best cases will lead to increased complexity of the protocol, which we also want to avoid. We try to keep our protocol pretty simple. We also want the execution time to be similar on similar platforms. We have a target hardware at Near, but we want people to be able to run our nodes on almost any 4-core CPU plus 16 gigabytes of RAM machine. So we don't want the execution time to vary drastically across different platforms. And finally, big challenge with determinism is how do you decide what are your fees? And this is a completely separate topic that I'm going to get to soon. Oops. Sorry, skip the slides. There are performance challenges with virtual machines. So one of them is the time to start. It's just the time that it takes for your virtual machine to warm up before it starts running the smart contract. And there are multiple factors that contribute to time to start. One of them is this deserialization time. So it doesn't matter what kind of deserializer you use. to store your compiled module. And there is also the contributing factor of the I/O cost. So in most cases, you're probably not going to be storing your compiled module in the memory. You're probably going to be storing it on the disk. So the time that it takes to load it is a big contributor to the execution time on a smart contract. The loading of the module also depends on many variables in your virtual machine. And in your smart contract, it depends on the size of the code. It depends on the size of the data section in your Wasm. Number of the methods in Wasm, surprisingly, also frequently contribute to the time it takes to load the module. And obviously, number of the imports also contribute to that. Then cold contracts is a big problem. Someone can deploy a contract and that they never call for many years, and then they try to call it 2 years later. And it can be living in your cold storage. So the question is, do we separate cold and hot storage in a blockchain is a pretty big question. Right now we don't, which means that the fees for the cold contracts dictate the fees for all of the contracts. But in the future, we might start separating them because certain contracts are going to be executed all the time, like exchanges, and we want them to be cheaper than contracts that executed very rarely. And finally, the compilation time. The compilation time is a challenge. Even with single pass and streaming compilers, compilation takes slightly different time. And so what we had to do, we had to go all over the Wasmer code and remove things like randomly seeded hash maps and like some multi-threading to make the compilation time consistent. Yeah. So there are also safety. Oh, wait, 1 second. My presentation is lagging. I'm sorry for that. Yeah, so finally, how do we decide the fees? So this is the big problem for every blockchain, because obviously every operation on a blockchain should take certain amount of money, right? You don't want stuff to be executed for free on your blockchain. So how do you decide what costs what? And especially when it comes to the virtual machine that has a very complex internal mechanisms. So the way many blockchains address it, they either do the educated guess sometimes, because if you have host functions which are cryptographic primitives, you might be able to guess how much it should cost. But most of the time, the way blockchains do it is by running time-based benchmarks. Like they execute operations over and over and over and time them and determine based on the timing how much they should cost. So we found out that this is not as precise as we want it to be. Very frequently, time-based benchmarks, even when they run for days, produce very high spread of execution time for the same fees. And so what we did, we took a big part of our node, which is runtime and RocksDB and virtual machine, and we're running it on the CPU emulator, QEMU. And I told you we also removed a bunch of the sources of non-determinism. And so now we just count the actual CPU instructions that our node takes to execute those various operations. And we were able to achieve precision and reproducibility for most of the fees to be within 5%. And for a couple of fees that are specifically involved with I/O, it's within 10–15% precision, which I think is a good result. I mean, estimating the fees is still very difficult. Well, first of all, something that we haven't addressed yet is the different CPU operations obviously have different complexity and different execution time. We do treat them the same right now. We ran lots of fuzzing to make sure we're not abusable in this way, that someone cannot really easily construct a contract that abuses certain CPU operation. Also, I/O operations are really difficult to benchmark and assign the fees to. It's well known that benchmarks for SSDs are especially tricky. So we don't even try to write our own SSD benchmark. We use third-party benchmarks to estimate it. And finally, I mean, just running things in emulator is extremely slow. And we do want to run stuff for many iterations, even inside emulator, for several reasons. One of it is just to reduce the volatility in case we forgot, some of the randomly seeded hash maps and stuff like that. But another one is to catch the corner cases. So we try to generate a wide array of the input, and just to make sure we didn't forget some of the corner cases that can have a disproportional computation time, that our fees are actually deterministic. So yeah, fees are tricky. Then, as I promised, I want to talk about the gas injector. As we know, instrumentation for WebAssembly is quite expensive. For some cases, if you use Wasm utils, which is one of the most popular instrumentation libraries out there, the CPU instructions caused by the instrumentation code itself can be 95% of the CPU instructions of the entire smart contract. So the instrumentation can be dominating the cost of running the smart contract. And this is mostly because the go-to instrumentation approach right now is to inject host function call on every Wasm block, which is of course expensive because you're crossing guest and guest host boundary every Wasm block. And so what we did here, we looked at what Wasmer 2 is doing, and what they do is they inject a global variable that they modify without crossing the host guest boundary. And they just modify it on every Wasm block, and they do this injection in their middleware. So we took the same approach. We just modified Wasm utils in our fork to do this kind of instrumentation. So any blockchain that uses Wasm, you guys are welcome to use this modified Wasm utils. It allows us to reduce the cost of running Wasm smart contracts 4 times, according to our most recent benchmarks. And also, it doesn't tie you to any specific WebAssembly virtual machine. So that's why we're not using Wasmer's version of this instrumentation, because we wanted to also work Wasm time and other kind of virtual machines, because instrumentation needs to be VM agnostic. Unfortunately, gas injector design does leak into the protocol spec, not something that we wanted to have. And this is because when you inject a different amount of WebAssembly code into your WebAssembly smart contract, now your contract might run out of memory earlier or later, or like might hit the stack size limit earlier or later. So it does kind of leak into the protocol spec, which is quite unfortunate. We haven't figured out what to do with it yet. But the good news is that you can actually write very suboptimal gas injectors. At least at Near, we don't do gas injection upon the contract execution. We do it upon the contract deployment. And the contract compilation and contract deployment is already quite expensive. So you can run a very simple and suboptimal gas injection there, and don't worry too much about its performance. Yeah. So as I said, we have a whole bunch of languages, currently 4, that have SDKs either pending or already being used for quite some time by the community. Interestingly, for Rust, we did have some requests from the community to have STD and no-STD versions of the SDK. Most of the time, community actually wants to use STD version of Rust SDK because they do want to import lots of Rust libraries, and not all of the Rust libraries support no STD mode. And so we had to really optimize an STD version of Rust SDK. And there are also alternative libraries written by the community that you can use. The cool thing about languages that do not have manual memory management, like AssemblyScript and Grain, is that you can actually just turn off the garbage collection, because the contracts, as I said, are short-lived, and we can totally afford allowing them using many megabytes of memory if they need to, without deallocating it. So that's an upside of using languages like that. And actually, we haven't made our mind whether we're gonna support garbage collection on the protocol level yet, because I mean, garbage collection is coming to the WebAssembly spec. So we have an opportunity to support a garbage collection on a protocol level, but we haven't made our mind yet about it. We had to do lots of SDK side optimizations because people writing contracts on Near, they want their contracts to be smaller in size because that means the fees are going to be smaller for compiling such contracts or for executing such contracts. Technically, it is possible to run extremely tiny contracts on Near if you use Rust. If you do not use STD and if you use all the best guidelines for writing tiny code, you can actually have less than 1 kilobyte contracts once they compile to WebAssembly. But your developer experience will suffer greatly. So most of the projects, even projects that care a lot about the performance and about the size, they actually still use our SDKs with STD. So the main contributors to the size actually for these contracts turn out to be obviously strings, errors, and you also got to be very careful with STD because it has different code for x86 and Wasm. So you want to sometimes dive into the STD implementation and make sure that when you compile to WebAssembly, you're compiling exactly what you want to compile because it can be a completely different code. And the other interesting thing is that we don't actually use all of these cool tools that WebAssembly ecosystem has for optimizing the WebAssembly, like Wasm opt and Wasm snip. And mostly because we don't want our developers to shoot themselves in the foot. Wasm snip is a very aggressive tool, and someone can accidentally overdo contract optimization and just cut too many things. So we just don't advise our users on using it. Yeah. There are interesting things to be said about using Wasm tailored languages like AssemblyScript and Grain. They have pros and cons. So pros obviously is that they're made to be efficient when compiled to WebAssembly. As I said, like AssemblyScript even has a self-hosted compiler. Like you can compile AssemblyScript with AssemblyScript, which is amazing. And Grain was designed specifically to be efficient when compiling to WebAssembly. So it means you can write, in some cases, highly optimized contracts with AssemblyScript and Grain. The disadvantages, of course, of these languages is that they still have small community. That means you have very few libraries. And it's still the case that when you want to write a smart contract in AssemblyScript, you need to import AssemblyScript library. Like you cannot, at least not on Near, you cannot import a library written in another language and compile to WebAssembly yet. We haven't enabled this a possibility yet. And also they haven't been battle proven, unlike Rust, that large companies like Google and Mozilla are using for their browser development. AssemblyScript and Grain haven't been battle proven, so we just don't advise our DeFi projects on using them yet. The other interesting thing is that we learned quite a bit from Ethereum experience with WebAssembly. We like the idea of the execution environments in Ethereum. And while we don't exactly have execution environment, we have several layers of virtualization. People can run Solidity contracts on Near because our EVM, which is Sputnik VM, is just a WebAssembly smart contract that runs on top of our WebAssembly virtual machine. And so people can already run up to 4 million gas contracts inside our EVM. And very soon, this number is going to increase by several X, maybe 4X, that will allow you to run pretty much any transaction that you can run on Ethereum on Near without any constraints. And we haven't even piped the host functions from all of the host functions from the EVM into our host functions. So many of the host functions inside the EVM are actually run in WebAssembly, which makes it quite suboptimal, but it still works. And obviously, like Rust, AssemblyScript, and Grain and Zig, they're all executed as the first-class citizens without extra layers of virtualization directly on our Wasm virtual machine. Finally, I wanted to tell you how we're planning to test these contracts. So we do have already quite a few testing frameworks that various projects used to test WebAssembly contracts on Near. But we came up with this cool idea of having a unified testing approach to any kind of contracts that people are deploying on Near blockchain. And this is achieved by basically testing WebAssembly contracts like they were live contracts. So you would take tests and you would compile it together with the contract code in such a way that the tests themselves are basically your contract host functions. Then you would deploy this stuff to your node, and then you would interact with tests as if there was contract functions, which allow you to unify lots of the experience around the running the contract code and make your testing experience as close to production as possible. So your code in tests is going to be highly reproducible in a production too. So that was it. That was not a very long presentation, but if you have any kind of interest in Wasm languages, if you like not just Grain and Zig, but there are other languages that you like and you want them, and you want to build an SDK for them, or you like some WebAssembly virtual machine, a compiler, please write us, and we might give you a grant to work on it. So thanks, everyone. Are there any questions in the chat?
So thank you so much, Maksym. That was very interesting. And we have one question. Why would you need to support that many languages? Isn't Rust enough for all purposes?
Well, so Near is developer-focused blockchain. So we want people coming to Near to have zero barrier when they develop on us. And developers have all kind of backgrounds. Some people used to work mostly with C++. Some people used to work with Python. So we don't want to force them to use Rust. We want them to be able to come to Near and just find whatever language they've been using all their life as a language that we support and start developing on it. Yeah, it's basically reducing the barrier for the developers. That's the goal. But also we like supporting open source projects. Like we're sponsoring AssemblyScript, we're sponsoring Grain and Zig and Wasm. So why not help all these languages if we can?
It's amazing to hear that you're helping those projects, like they really need it, and it's great for developing the whole infrastructure of the ecosystem. The next question, do you have any plans for enabling cross-shard contract-to-contract interaction?
So this is something that's been working from the start. So right now we have a single shard, but in test environment, we're running like 8 shards, and we're gonna roll out 8 shards very soon in the next couple of months. So this is not something that we add later. This has been already built in from the start. When people develop smart contracts on Near, they don't even think which shard the smart contract is running on. This is very similar to how you write JavaScript programs. Like when you write JavaScript program and use promises, you don't think which CPU core is running which part of your JavaScript program right now. You just use promises and it somehow gets executed behind the scenes. So it's very similar to when you write a decentralized app on Near and have various, and you have it partitioned in various contracts, or you interact with exchange or swaps. You don't even know, are they running on the same shard or are they running on different shards? And there is like no incentive in Near to collocate contracts on the same shard. We don't want to have any kind of perverse incentive for people to try to fight and co-host on the same shard with some exchange or something like that. It's all exactly the same fees, exactly the same finality time for cross-contract interactions when they talk either within the same shard or across different shards. And actually, in a year or two, we're going to enable dynamic resharding that is going to be rebalancing our shards to be of the same size. And in that case, even if you're on the same shard with some contract right now, in the next hour, it might change. And it might be resharded, and you might end up on different shards. So inherently at Near, there is no distinction on whether you're on the same shard or whether you're on different shards from the developer perspective.
Okay, thank you so much. I think that's it for the questions.
Thanks, everyone.
At least for now. Thank you so much, Maksym.